Right now, while you're listening to this, a fragile 2,100-pound piece of forged metal and vintage electronics is screaming through the pitch-black ocean of deep space at more than 38,000 miles per hour. It is currently over 15 billion miles away from Earth, a distance so vast that a beam of light takes more than 22 hours just to cross the void between us. It is powered by 3 decaying cylinders of radioactive plutonium that generate less electrical wattage than a small household desk lamp. Its radio transmitter emits a signal so unimaginably faint that by the time it reaches the massive dish antennas of NASA's Deep Space Network, the total energy harvested on Earth is less than a fraction of a billionth of a watt. Yet that tiny, solitary craft built in the mid-1970s, before the invention of the personal computer, is doing something that has thrown theoretical astrophysics into a state of profound confusion. For decades, every mathematical model of our solar system was based on a simple, comforting assumption. Scientists calculated that once a spacecraft escaped the gravitational grip of the sun and passed the edge of our celestial bubble, it would sail along an unyielding, predictable hyperbolic arc into the cold vacuum of the interstellar medium. According to Newton's first law of motion, an object in motion will stay in motion along a straight line unless acted upon by an external physical force. Because space outside our solar system was presumed to be a virtually empty void, Voyager 1's trajectory was supposed to be completely fixed, frozen in the geometry of celestial mechanics. Standard orbital mechanics said Voyager 1 could not and would not change its path. Standard physics was completely wrong. When NASA's tracking stations analyzed the long-term telemetry and Doppler shift measurements returning from the interstellar frontier, they detected something that defied decades of peer-reviewed predictions. Voyager 1 was not following the expected pristine trajectory. It was experiencing an unaccounted-for lateral deflection, a subtle, persistent shift in direction and orientation that broke standard calculations. In the ultra-thin plasma ocean beyond our sun's protective boundary, an unseen physical force was pushing against the spacecraft, deflecting its course and forcing telemetry controllers on Earth into a high-stakes diagnostic battle to save humanity's most distant ambassador. Before we dive into the data, hit subscribe to join our community of space enthusiasts, and drop a comment below letting me know which city or country you're watching from today. To understand why a trajectory shift in the absolute darkness of interstellar space is causing such shockwaves throughout the scientific community, we have to go back to the beginning. We have to revisit the golden age of planetary exploration, when human beings first dared to launch a message in a bottle into the cosmic ocean. The story of Voyager 1 begins in the late 1960s, inside the quiet offices of NASA's Jet Propulsion Laboratory in Pasadena, California. A brilliant young aerospace engineer named Gary Flandreau was tasked with mapping out potential future trajectories for deep space probes. While crunching orbital calculations by hand and using primitive mainframe computers, Flandreau noticed something extraordinary. In the late 1970s, a rare gravitational alignment of the outer planets was going to occur, a geometric phenomenon that happens only once every 176 years. Jupiter, Saturn, Uranus, and Neptune were sweeping into a single continuous arc on the exact same side of the Sun. Flandreau realized that a single spacecraft, if launched at precisely the right window, could utilize a technique called gravitational slingshotting. By skimming close to Jupiter, the craft could steal a tiny fraction of the giant planet's orbital momentum, accelerating the probe and bending its flight path toward Saturn. Saturn could then accelerate it toward Uranus, and Uranus toward Neptune. Without this cosmic assist, a voyage to the outer edge of our solar system would take more than 30 years using conventional chemical propulsion. With the Grand Tour alignment, that timeline could be cut by more than half. NASA mission planners seized the opportunity and designed the twin Voyager spacecraft. Voyager 1 lifted off from Cape Canaveral on September 5, 1977, aboard a colossal Titan IIIe Centaur rocket. Though launched 16 days after its twin, Voyager 2, Voyager 1 was placed on a shorter, more direct trajectory designed to reach the gas giants first. The primary objective for Voyager 1 was not just to photograph the giant planets, but to answer a specific, high-stakes question about the architecture of our solar system. Mission directors sacrificed any chance of Voyager 1 visiting Uranus or Neptune in order to target a dangerously close flyby of Saturn's largest moon, Titan. At the time, astronomers knew Titan possessed a thick, mysterious atmosphere, but they had no idea if its surface harbored oceans of liquid methane or organic precursor chemicals. Voyager 1 barreled past Jupiter in March 1979, capturing breathtaking images of swirling atmospheric storms, active volcanic plumes on the moon Io, and the delicate ring system surrounding the gas giant. It then accelerated toward Saturn, making its historic rendezvous in November 1980. The probe skimmed just 4,000 miles above Titan's orange haze layer. That was a success. Titan was revealed to possess an atmospheric surface pressure higher than Earth's, saturated with complex hydrocarbons. But that single aggressive flyby came at a heavy orbital price. The immense gravitational pull of Saturn and Titan acted like a giant cosmic slingshot, snapping Voyager 1's trajectory upward out of the ecliptic plane, the flat disk where Earth and the other major planets orbit the Sun. Voyager 1 was catapulted northward at a 35-degree angle relative to the plane of the planets. It was fired into the cosmic unknown, traveling along a path that no human craft had ever traversed. For the next 32 years, Voyager 1 zoomed through the dark, lonely outer reaches of the solar system. Scientists calculated that the probe was heading toward the boundary where the Sun's influence finally surrenders to the vast ocean of the Milky Way galaxy. To understand what Voyager 1 encountered, you must first picture the invisible structure that houses our entire planet. Our Sun is not an isolated star sitting quietly in a vacuum. It is a fiery nuclear furnace that constantly exhales a violent, supersonic stream of charged particles, mostly protons and ionized electrons, known as the solar wind. This solar wind blasts outward at speeds ranging from 700,000 to nearly 2 million miles per hour. As this energetic wind pushes outward, it carves out a massive, teardrop-shaped protective cavity in the interstellar medium. This cavity is known as the heliosphere. The heliosphere is our cosmic home. It encapsulates Earth, Mars, the gas giants, and the distant frozen realms of the Kuiper Belt. Think about what that actually means for a second. Outside our heliosphere lies the very local interstellar medium, a vast, turbulent cosmic ocean filled with the remnants of ancient supernova explosions, interstellar magnetic fields, superheated plasma, and high-energy galactic cosmic rays moving at near light speed. Where the solar wind meets this galactic ocean, a violent collision occurs. Here is how to picture it. Imagine a high-powered water fountain running at full spray inside a fast-flowing river. Near the fountain nozzle, the stream of fresh water pushes away the muddy river water, creating a clean, turbulent air and water bubble around itself. That clean bubble is the heliosphere. The surrounding river water, trying to collapse back inward, is the interstellar medium. The exact boundary line where the outward force of the fountain water balances the inward pressure of the river current is called the heliopause. For decades, theoretical astrophysicists modeled the heliopause using computer simulations. They assumed the transition would be broad, gentle, and quiet. They expected the solar wind to gradually taper off into nothingness over billions of miles, allowing Voyager 1 to slip into interstellar space without encountering any major resistance. They were fundamentally mistaken. On August 25, 2012, at a distance of roughly 121 astronomical units, over 11 billion miles from Earth, Voyager 1 became the first human-made object in history to cross the threshold into interstellar space. But the boundary it crossed was nothing like what the textbooks had predicted. As Voyager 1 approached the heliopause, its onboard instruments recorded a sudden, sharp surge in high-energy galactic cosmic rays coming from deep space. Simultaneously, the detection of lower-energy solar particles generated by our Sun plummeted to near zero. Not a metaphor, not a technicality. Voyager 1 had physically punched through the outer wall of our solar system. When researchers analyzed the telemetry returned by Voyager 1's magnetometer and plasma wave subsystem, they realized they were looking at a radical break from standard solar physics. Rather than entering an empty, serene vacuum, Voyager 1 found itself bathed in an interstellar environment characterized by extreme density jumps, violent plasma oscillations, and unexpected magnetic fields. Because Voyager 1's primary plasma science instrument had stopped functioning back in 1980, scientists had to use an ingenious alternative method to measure the density of the interstellar space around the probe. They relied on its plasma wave subsystem, which utilizes two long, whip-like electric field antennas to detect minute oscillations in surrounding ionized gas. Whenever the Sun erupted with a massive coronal mass ejection years earlier, those high-energy solar shock waves would eventually travel billions of miles to the edge of the heliosphere and slam into the interstellar medium outside. These collisions caused the interstellar plasma to vibrate like a struck bell. When Voyager 1 picked up those plasma oscillations, the data revealed something astonishing. The density of ionized gas outside the solar system was not lower than inside the heliosphere. It was more than 40 times higher. Voyager 1 was swimming through a thick, magnetized, high-density plasma ocean. And that is where the deep space anomaly began. According to theoretical physics models, the interstellar magnetic field outside our solar system should have been tilted at a dramatic angle relative to the magnetic field generated by our Sun. Scientists expected Voyager 1 to detect a dramatic rotation in the direction of magnetic field lines the instant it crossed the heliopause. Instead, the magnetometer data sent back by Voyager 1 showed that the interstellar magnetic field was running almost completely parallel to our Sun's internal magnetic lines. It was as if the interstellar magnetic field was being forced to drape around the nose of our heliosphere like fabric stretched taut over the bow of a moving ship. Then came the trajectory calculations that left NASA engineers utterly speechless. When mission controllers at the Jet Propulsion Laboratory tracked Voyager 1's precise location using the Deep Space Network's global network of massive radio antennas, they noticed subtle, unaccounted for deviations in the spacecraft's expected pathway. Voyager 1 was not traveling along a purely unperturbed ballistic trajectory. Something in deep space was gently but persistently pushing against the probe, deflecting its orientation and imparting a subtle transverse drift. Think about what that actually means for a second. A spacecraft that weighs nearly a ton, traveling through what was supposed to be empty space at 38,000 miles per hour, was being deflected by environmental forces that standard science claimed shouldn't exist. To understand where this mysterious force was coming from, astrophysicists turned to complex peer-reviewed papers published in academic physics journals. The data pointed to a phenomenon known as magnetic draping and interstellar plasma pressure. The heliosphere is not stationary. Our entire solar system is moving through the local interstellar cloud at roughly 45,000 miles per hour. As our cosmic bubble plows through the interstellar medium, superheated plasma and dense interstellar magnetic fields stack up against the outer wall of the heliopause. This creates a high-pressure zone, a massive cosmic bow wave. The interstellar magnetic field lines wrap tightly around the heliosphere, creating a localized magnetic gradient. Furthermore, measurements taken by space observatories like NASA's Interstellar Boundary Explorer, or IBEX, detected a massive, unexplained feature running across the edge of our solar system, a glowing band of high-energy neutral atom emissions known as the IBEX ribbon. The direction of the interstellar magnetic field measured directly by Voyager 1 was inconsistent with the global models derived from the IBEX ribbon observations. Astrophysicists realized that Voyager 1 was passing through an intense, highly localized magnetic boundary layer, a region where the immense pressure of compressed galactic magnetic fields and superheated plasma currents exerts a physical force on anything floating through it. The space outside our solar system is not a passive void. It is a dynamic, highly pressurized, magnetized ocean. Voyager 1 was literally being pushed around by the turbulent current of interstellar space. However, as if surviving a cosmic magnetic storm wasn't enough, this physical deflection triggered a terrifying mechanical crisis aboard the 49-year-old spacecraft. A crisis that brought NASA engineers to the brink of losing Voyager 1 forever. Here's the part nobody is talking about. For Voyager 1 to communicate with Earth across a distance of 15 billion miles, its 12-foot wide dish antenna must point toward home with incredible precision. The radio beam transmitted by Voyager 1 is extremely narrow, focused like a tight pencil beam of light. If the spacecraft tilts or drifts away from Earth by even a fraction of a single degree, the radio signal misses our planet entirely, sweeping past Earth into the dark void. If that happens, communication is permanently lost, and Voyager 1 becomes a dead piece of drifting space junk. To keep its antenna locked onto Earth, Voyager 1 relies on an attitude control system powered by tiny hydrazine thrusters. These thrusters don't fire continuously. Instead, they deliver tiny, split-second puffs of gas, lasting just tens of milliseconds, to counteract natural drift, nudging the spacecraft gently back into alignment whenever it strays. Under normal conditions, Voyager 1 would fire these thrusters roughly 40 times a day. But as the unexpected interstellar magnetic drag and plasma pressure pushed against the spacecraft, its orientation drifted far more rapidly than planned. The attitude control system had to work overtime, firing thrusters more frequently to maintain its critical alignment with Earth. And that is when decades of physical degradation caught up with the probe. Inside Voyager 1's fuel tanks, a rubber diaphragm separates the liquid hydrazine propellant from the pressurized nitrogen gas that forces the fuel into the thruster lines. Over nearly half a century in space, that rubber diaphragm has been slowly breaking down. As the rubber degrades, it releases a chemical byproduct that reacts with a hydrazine to form microscopic particles of silicon dioxide, essentially tiny grains of glass. For years, these microscopic silicon dioxide particles traveled down the fuel lines and began accumulating inside the narrow fuel tubes, feeding Voyager 1's attitude control thrusters. The fuel lines were clogging. By 2002, the fuel lines feeding Voyager 1's primary attitude propulsion branch were so severely restricted that NASA engineers had to switch to a secondary branch of attitude thrusters. By 2018, 16 years later, that second set of thruster lines began showing signs of severe clogging as well. Desperate to keep the spacecraft alive, flight controllers at JPL performed a high-risk engineering feat. They decided to turn off the attitude control thrusters entirely and activate Voyager 1's trajectory correction maneuver, or TCM thrusters. The TCM thrusters were larger, thrusters located on the back of the spacecraft, originally designed to perform orbital adjustments during the planetary flybys of Jupiter and Saturn. They had not been fired since November 8, 1980. when Ronald Reagan had just been elected President of the United States. To fire a set of thrusters that had sat completely frozen and dormant in the vacuum of deep space for 37 years was a terrifying gamble. Engineers at JPL had to dig through yellowed, 50-year-old paper documentation and decipher code written in an obsolete assembly language used in the 1970s. They calculated that the TCM thrusters could only be safely activated if a set of small internal heaters were turned on first to warm up the frozen propellant lines. But Voyager 1's power budget was already running dangerously low. Voyager 1 does not use solar panels. At 15 billion miles from the sun, sunlight is thousands of times fainter than on Earth. Instead, the probe relies on 3 radioisotope thermoelectric generators, or RTGs. These RTGs generate electricity from the heat released by the natural radioactive decay of plutonium-238 pellets. Plutonium-238 has a half-life of 87.7 years. Every single year, radioactive decay combined with the physical degradation of the thermocouples strips away roughly 4 watts of electrical output from the spacecraft. When Voyager 1 launched in 1977, its RTGs generated 470 watts of electricity. Today, that power level has plummeted by more than half, leaving the spacecraft operating on less than 200 watts, barely enough power to run a couple of standard light bulbs. To turn on the thruster heaters without overloading the power grid and causing a total system shutdown, engineers had to turn off crucial survival heaters elsewhere on the spacecraft. They sent the commands across the void, waiting 19 nerve-wracking hours for the signal to reach Voyager 1, and another 19 hours for the telemetry confirmation to travel back. On December 1st, 2017, the confirmation finally hit NASA's Deep Space Network dishes. The 37-year dormant TCM thrusters had fired flawlessly. They gave tiny split-second pulses, successfully reorienting Voyager 1's dish toward Earth. That was a success, but the victory was short-lived. Fast forward to 2024. After 6 years of continuous use in interstellar space, the fuel lines inside the trajectory correction maneuver thrusters had become clogged with silicon dioxide, too. And this time, the clogging was far worse than anything engineers had seen before. The thrusters were struggling to generate enough force to counteract the persistent interstellar drift and keep the antenna locked on Earth. Voyager 1 was running out of options. The primary attitude thrusters were clogged. The secondary attitude thrusters were clogged. The TCM thrusters were clogged. If NASA couldn't find a way to clear or bypass those lines, Voyager 1 would lose its lock on Earth within weeks, drifting alone into the interstellar night forever. JPL engineers devised a daring, high-stakes operational plan. They decided to switch Voyager 1 back to one of the original attitude propulsion thruster branches that had been abandoned back in 2002. However, because the spacecraft had lost so much electrical power over the intervening 22 years, that old thruster branch was now completely frozen solid. Its heaters had been turned off years ago to conserve electricity. If engineers tried to send liquid hydrazine through a frozen thruster, the fuel would instantly freeze, rupture the lines, and destroy the spacecraft. To make matters worse, Voyager 1 was so low on power that it didn't have enough electricity to turn on the thruster heater without turning off one of the spacecraft's remaining irreplaceable science instruments. Project manager Suzanne Dodd and her team at JPL refused to give up on a science instrument. Instead, they scrutinized every single watt of electrical flow on the spacecraft. They calculated that if they turned off one of the spacecraft's primary main heaters for just 1 hour, they could temporarily redirect that tiny pocket of electricity to warm up the dormant thruster branch. It was a terrifying tightrope walk. If they left the main heater off for too long, vital onboard electronics would freeze and die in the near absolute zero environment of deep space. If they didn't leave it on long enough, the thruster would remain frozen and explode upon activation. On August 27, 2024, engineers executed the command. They turned off the main heater, warmed the old attitude thruster for 60 minutes, and commanded Voyager 1 to fire. 39 agonizing hours later, the telemetry hit the radio dishes in Goldstone, California. The command had worked. The legacy attitude thruster fired, clearing its clogged tube and restoring Voyager 1's precise pointing capability. Against all odds, human ingenuity operating from 15 billion miles away had saved our farthest scout once again. This incredible remote engineering rescue is not just a story of technical triumphs. It has profound, life-altering implications for our understanding of life on Earth and the future of human civilization. It is easy to look at Voyager 1's journey as an abstract scientific experiment, a piece of metal measuring invisible magnetic fields in a cold, distant void. But the data Voyager 1, transmitted back from the edge of the heliosphere, reveals something critical about our very survival on Earth. The deep space outside our solar system is perpetually bombarded by violent galactic cosmic rays, highly energetic atomic nuclei stripped of their electrons and accelerated to nearly the speed of light by cataclysmic events like supernova explosions and supermassive black holes. If those galactic cosmic rays were to strike Earth's upper atmosphere unhindered, they would strip away our ozone layer, shower the surface with ionizing radiation, mutate biological DNA, and render life on Earth nearly impossible. Voyager 1's direct in situ measurements prove that our heliosphere acts as a gigantic biological shield, deflecting and blocking up to 70% of all lethal galactic cosmic rays from ever reaching the inner solar system. Think about what that actually means for a second. Our sun is not just a source of light and heat. Its supersonic solar wind creates a dynamic magnetic cocoon that shields our planet from the lethal radiation ocean of the Milky Way galaxy. We are traveling through a radioactive galactic wasteland inside an armored solar-powered magnetic fortress. Understanding the complex plasma dynamics and magnetic deflection zones mapped out by Voyager 1 is also vital for the future of human space exploration. As humanity prepares to construct permanent outposts on the Moon, send crewed missions to Mars, and eventually venture toward interstellar targets, we must navigate the space weather beyond our home bubble. Voyager 1 has given us our very first localized weather report from interstellar space. We now know that interstellar space is not uniform. The heliosphere actually breathes, expanding and contracting in dynamic 11-year cycles driven by the solar cycle. When solar activity peaks during solar maximum, the intense solar wind inflates the heliosphere, pushing the heliopause outward into interstellar space. When solar activity drops during solar minimum, the immense pressure of the interstellar plasma ocean pushes back, compressing the boundary inward. Voyager 1 showed us that the boundary of our solar system is a dynamic, living front line. Today, Voyager 1 continues its solitary journey through the interstellar ocean. It did not stop. It is traveling further from home every single second, covering more than 320 million miles every year. However, the clock is ticking down toward an absolute physical threshold. Despite the heroic efforts of engineers at JPL, the plutonium-238 inside the spacecraft's RTGs is decaying second by second. To manage this relentless drop in power, NASA has systematically shut down instruments over the past decade. Engineers have turned off the cameras, the ultraviolet spectrometer, the infrared sensor, and the subsystems that aren't critical to interstellar field measurements. By the late 2020s or early 2030s, electrical power will drop below the absolute minimum wattage required to operate the primary radio transmitter. On that day, the final whisper of a telemetry from Voyager 1 will travel across the void, taking more than 22 hours to strike the radio dishes of the Deep Space Network. The signal will flicker out, and Voyager 1 will drop into permanent, unbreakable radio silence. Yet silence is not the end of its journey. In the pristine vacuum of interstellar space, there is no atmospheric friction, no moisture to cause corrosion, no oxygen to oxidize metal, and virtually no dust particles to erode its physical frame. The structure of Voyager 1 will remain almost perfectly preserved for hundreds of millions, perhaps billions of years. In roughly 40,000 years, Voyager 1 will drift within 1.6 light-years of the star AC +79 3888, a red dwarf star in the constellation Ophiuchus. In about 300,000 years, it will pass deep within the realm of the star Sirius, the brightest star in our night sky. Long after our sun expands into a red giant billions of years from now, long after the oceans of Earth evaporate and the monuments of human civilization crumble to dust, Voyager 1 will continue orbiting the center of the Milky Way galaxy, a silent, indestructible artifact of a species that dared to look up at the night sky and reach out into the unknown. Mounted on the side of Voyager 1 is a famous 12-inch gold-plated copper phonograph record, the Golden Record. It contains 115 images encoding the story of Earth, diagrams of DNA, images of human anatomy, landscapes, rivers, animals, architecture, and mathematical equations. It holds spoken greetings in 55 human languages, the sounds of ocean waves, thunder, bird calls, footsteps, a heartbeat, and brainwaves recorded while thinking of love. It carries musical compositions spanning human history, Mozart, Bach, Beethoven, traditional folk music from across 6 continents, and Chuck Berry's Johnny B. Goode. When NASA launched Voyager 1 in 1977, scientists thought they were sending a simple planetary probe to photograph gas giants. They thought they were asking basic questions about celestial mechanics and planetary ring structures. In reality, Voyager 1 taught us something far deeper about our true place in the cosmos. It proved that human curiosity is not bound by the gravitational pull of our homeworld. It showed us that a tiny machine, built with technology less powerful than a modern key fob, can cross billions of miles of dark vacuum, punch through a superheated magnetic boundary, survive in the interstellar dark, and redefine our fundamental understanding of physics. We live on a tiny pale blue dot suspended in a vast, dark, radioactive ocean. Yet we have constructed an object that will outlast our planet, outlast our star, and perhaps outlast our entire species. Voyager 1 is out there right now, cold, silent, and flying at 38,000 miles per hour through the interstellar dark, carrying the memory of who we were, what we felt, and how far we reached. What do you think about Voyager 1's incredible journey into the interstellar ocean? Does knowing that a piece of human engineering will outlast our solar system change how you view our place in the universe? Let me know your thoughts in the comments below. Thanks for watching, and stay curious.